Hi, I would like to talk about graph attention network, specifically how it relates to graph convolutional network and how to create a forward method using Pytorch. As of course, what we will talk about, I assume that you understand what are graphs and you understand the basics of machine learning because it's an implementation video. We will talk what are graphs, like what are the benefits of graph and what are the requirements of a graph neural network to use these benefits. Like what is exactly what this convolution means in terms of graph neural networks and how it relates to connectivity. For our derivations or interpretation, I will show like few useful tricks, and we will discuss how to implement graph convolution network and then improve it using attention mechanisms to create a graph attention network. Okay, so the question, what are graphs? What are the benefits of graph? Well, graphs are mathematical structures that store information about objects. Objects we call nodes. They have a unique, some kind of name. I will just refer n1 and 2 ... right, in some specific order. And these objects, nodes, they have relations to other nodes given as edges. Typically, it's just a it's a tuple of either, well, in most cases, it's just node names. Node 0 and 1 connected, and so on, so on and so forth. Well, these edges, they may have weights, some kind of attribute, but we won't use them. Also, they may have directions. We will ignore it. We will just say that if there's an edge, it connects both ways. One addition, there may be self loops. Here, for example, node 1 is connected node 4, but it also has a self loop. We will use it also. So there are different parameters, tools. It's a developed, of course, field. Specific vocabulary, I don't know what is degrees or adjacency, and actually Laplacian. What I wanted to talk, there's one useful tool called an adjacency matrix. This is a matrix that stores, it's a matrix n by n matrix that stores as basically as a mask connections, nearest neighbors of each node, right? And it looks something like this. So you should interpret this adjacency matrix as n by n matrix, and that each row of this matrix holds information about basically row number 4 stores information about neighbors of this node. For example, node 4 is connected to node 1. Maybe we'll return to the graph, to node 2, node 3, but not to itself. That's what we see. One little peculiarity here is self connections. For some reason, they are assigned double the weight. Maybe again, it can be interpreted. We won't use the double weight, but again, if we take a node 1 and its neighbors, this self loop kind of looks like two edges going out, right? Maybe that's why. So okay, this adjacency matrix encodes the neighborhood, the nearest neighbors of nodes as rows. That's the main takeaway. Although there are different other useful matrices and representations, we will use only one and not use the others. So the main strength of graphs actually are these connections, neighbors, connectivity, and they present like a different view on data, or provide the option to examine like the connections between large number of objects. And so naturally we have to use it to our benefit somehow. I mean, of course there are methods, but this is the main idea of a graph neural network, that we can leverage this connectivity. Well, the problem for graph neural network is that graphs are not exactly structured well. Their data is not particularly well represented as metrics, because there's, even for one graph, you can define it in many other ways, right? These naming conventions, whatever we call node 1 or node 2, it doesn't matter. Actually, we can replace them and pass them in different order, right? And because we just pass it in different order, the rows of these matrices will be swapped. So basically, adjacency matrix will look different. I didn't talk, but okay, we may hold information about each node may store some value. It should be a numerical value. Typically, it's a vector. But again, let's say it's a number, so we can create some kind of storage of features. I will call it H because it's called so in neural networks, probably because it's hidden state or something. But the idea is that each node, feature of each node is stored in an appropriate index of this matrix. Feature of node 1 will be stored at index 1. And again, if we swap the ordering of nodes, even if we examine the same graph, all this will change. Adjacency matrix will change. Our feature storage will change. So it's kind of problematic that our neural network has to be agnostic to such changes. Well, usually they're called permutation invariants. But then again, we may examine another graph. It will have not like 4 nodes, it will have a million nodes. It also should be invariant to that. It should work well for all the graphs. So it's kind of difficult. And we will describe how to do it. Again, main benefit is connectivity. That we, by examining each node and its neighborhood, we can distill some useful information. And this connectivity is closely related to convolution. Again, probably that's why it's in the name, because it does pretty much a convolution, only interpreted differently for graphs. But we can examine convolution for 2D images. I won't show you any example, but then just to understand that when we were working on images, this convolution kernel, it's very well defined. You can understand, interpret it easily. There are a few caveats, like number of neighbors of an image. It's not always 8. If you're sampling corners or edges, you will get fewer numbers. But still, in convolutional images, it can be like, you can fight with it, I don't know, just by applying padding. You can interpret it as adding ghost neighbors, and then you can apply the convolution, like every pixel has 8 neighbors, right? Well, here in this case example, it's a kernel of size 3. So basically it produces some operation. In this case, depends on your kernel, but in this case it just sums up all the numbers except the essential pixel, and just produces number of pixels, number of neighbors. Okay, but what would that mean in terms of convolution? I mean, graph. What would kernel mean? Okay, we kind of saw it in this adjacency matrix, because it stores information about nearest neighbors. So clearly it can be used. But like, what does it mean to have a radius of 2 or 3 for graph? We will touch on this in a few minutes. But if we return to convolution on images, we can interpret it as some kind of exchange of information, of diffusion of information. That depends, of course, like how you view it, either from view of this central pixel or its neighbors, whatever. But then when you change a kernel of a convolution on image, it basically gathers information from farther and farther. If you look at inversely, you can say it propagates information to the furthest neighbors. Again, what would it mean for a graph to have a size of 7, right? It's not clear. Well, the alternative idea is that you can basically do the same, only using a smallest kernel, but then apply convolution, cross correlation, whatever, repeatedly, and you achieve basically the same result. It's not mathematically the same, but the main idea is that you propagate or sample information from the furthest neighbors. So we can return to this question of graph size for a graph, kernel size for a graph, right? Here's one semi kind of joke example. When I ask, okay, given like 3 steps from starting from a node, like where you will end up, right? And you can draw all the possible paths as trees. And you can observe that for this particular structure of a graph, it will mostly stay in this region where it started, and very rarely will go the full path, the max length. So it's kind of not clear. It is closely related, right, to kernel size, but then what does it mean that you sample? When you sample the same point multiple times, right? It's kind of open question. But again, we can use simple approach, is that we use a small kernel but do multiple iterations. So that's the main idea, that actually we can use the adjacency matrix for determining the nearest neighbors and do some sampling somehow that involves the adjacency matrix. But in order to discuss it, to show the basic interpretations in derivation, I would like to view a few linear operations in an alternative way that I will use. They're kind of hacky. I don't know, fake, tricky, I don't know. But then let's say we have a matrix that multiplies some vector. This matrix is, I don't know, some kind of transformation. Here it's just some random collection of zeros and ones. And then what I propose is that you replace this matrix as a container, as a vector of columns in this case, right? And what you end up is like it's like a dot product. And actually this cheat, this hack kind of works miraculously. I don't know. You get the same result. Of course, it kind of is true. This operation, I mean, storing vectors inside vectors, probably not correct idea, but underneath it's a proper operation in this particular case. Like it is heavily inspired from interpretation when you solve system of linear equations, and you might hear something along the lines of like the columns of this matrix T do not span the space of whatever vector on the right. And given that this looks like a matrix equation and the middle vector is like your unknowns. And so with the interpretation in that case that these unknowns, in this case they are knowns, right? But they are just coefficients for columns of matrix T, right? And you construct the linear combination. So it's kind of, it's not completely false. It's just these operations between these vectors of vectors and the right vector. It's like, it's not very properly defined. We can view it as in a transposed representation. We just transpose both sides. Of course, nothing changes. Of course, in this case, interpretation changes, and we say that we are looking for linear combination of rows of this matrix. In this case, it's transposed matrix, but whatever. We're getting a linear combination. Here's a graphic example for it's easy to understand. And actually, we will use this transposed representation when we multiply on the right in this video, because its operations are defined so in Pytorch linear layer. Well, another trick, it's not trick, it's just a reinterpretation, is if we want to transform multiple vectors, we either can transform them one by one, or alternatively we can stack them into matrix, stack columns. In this case, I used like concatenation symbol, and then we see that basically if we apply transformation to this concatenated matrix, we get concatenation basically of transformed vectors, right? It's kind of a reinterpretation of a probably well-known fact. What's less known, at least for me, is that you can actually not transform many vectors, like million vectors at the same time, but you can transform one vector using multiple transformations, just by stacking transformation matrices together. It will be useful in multi-head graph attention network step. So that's about it about linear algebra, right? That we can kind of interpret matrices as rows. We will use it transposed representation, and that, you know, just we can transform a bunch of vectors at the same time or apply multiple transformations. Now we will actually use this to define a graph convolutional network. And based on this, we will define graph attention network. So as the name implies, convolution means some kind of aggregation of information, similar to convolution operation in images. So in this case, we have to gather information from node neighborhoods and some kind of collected and represent node as some kind of function of itself and its neighborhood in its neighbors. So that's the goal. Again, each node has a feature, and pretty much the same as we did here. We stacked node, some kind of parameters into a list. In this case, we stack basically these parameters as vectors, and we get this feature matrix H. And then if we are so eager to do neural networks to create, we can apply already a linear layer to it, not kind of to a whole matrix, or we just can view it as a application of a linear layer to each feature vector, right? In this case, I write it in transpose notation, multiply on the right, everything is transposed. Mostly because we will stack these feature vectors as rows. It's just easier to do linear algebra, and it's kind of defined so in linear layer of Pytorch, right? But then again, like using this approach, we just transform each feature into new feature. And so the question is like, what is the point? Kind of, we are not using actually the connectivity between nodes. And actually the proper way would be to first to gather information from each node. I guess we replace old feature vector with some aggregated variant of and then we apply the linear layer on top of it. So the question, how do you get this aggregated representation? So there must be some kind of function that takes in all the neighbors of features of neighbors of this node, and then it pixel like transforms into one feature vector, right? And again, we return to the problem that actually there are different ways to represent graphs. Each node may have different number of neighbors. Say even if the same graph, it can hold it in different order. So what are the functions that are actually invariant to this? Easiest examples are just summing them up, taking a mean or a maximum value. All of these are order invariant. In case of mean and max, I would say even maybe number of node invariant in a sense. And of course, sum and mean are related. It's not problematic. I want to take a look at this fake example and say we want to aggregate features of neighbors of node 1 into new value. And we just say that node has a neighbor 2 and neighbor 3. And you can basically say, okay, let's aggregate all the node features except with different weights, such that non-neighbors get 0 weight, neighbors get weight of 1. And well, you can express this in terms of kind of dot product, as we've seen in a linear algebra example. And actually this matrix, this row that we used for this kind of weights or masking is nothing else than rows of adjacency matrix. And so what you actually get, you get one row of H aggregated, is just a row of adjacency matrix times our feature matrix. That simply means that you can express this aggregation, simultaneous aggregation of all nodes via multiplication of A times H. And then we actually can solve this, and then we actually can apply actually neural network to these aggregate values and produce some whatever result you need, classification or whatnot. And there are a few caveats about like self loops. Self loops are important here and also in attention network, although they might not make any sense in practical in interpretation of data in our daily life, like someone interacts with itself. Okay, so this is the main idea. One may ask, all this talk about neural network being invariant to permutations and such, and then we use adjacency metrics and we are stacking features. Clearly, this is not permutation invariant. And it's true. The deal is probably you can view it as such that actually neural network is applied only to aggregated features. And aggregate features, it's in this case, it's okay, it's related to specific graph, right? But you just do it once before applying neural network, and then actually neural network just looks at each entry of aggregated feature of a node and then applies its metrics. Basically, it doesn't care how many times it does it. So it doesn't matter how many nodes there are. So that's the main idea. For convolutional network, you just do prior aggregation and then you apply neural network. It can be expressed as matrix multiplication. Now, what does the graph attention network do? Well, actually, it does the same. Here's the equation, except few steps. Here is the paper. I will scroll to the formulas. Well, we will focus on this stuff. I hate it when it copies it and scales it every time. Like I'm in 100% zoom. It should refer to that. So there will be this matrix E that has entries E, A, J. This matrix will be basically the same as adjacency matrix. So it's kind of will be reused in aggregation. That's the high level idea. How it will be defined. So in this case, our H's, they are kind of inputs. They are features of each node. And there's such a function A that for a relation of node I and J, it will take in its features and it will produce a scalar weight. Now, if you should mention that there's some kind of transformation going on before, so it will transform to some representation GI. And so the idea is, what is this function that generates these new weights? In this kind of is different approach to our adjacency. Adjacency 100% worked from the idea that we have edges somewhere, and these are just weights as mask basically. And the attention mechanism, what it is, it proposes, okay, we will generate some number, some scalar, a weight, only solely based on contents of both features. And again, it kind of simultaneously compares them, right? That's the idea. Well, authors additionally apply to these weights normalization. It's a softmax. If you don't know what is softmax, is basically it's an operation that transforms our weights into something that has properties of probability distribution. So it has a sum of all probabilities is equal to 1, and then all the probabilities are positive and non-negative. I would say, again, when you exponentiate anything, if you look at the graph of exponent, it is always non-negative, right? And there's this normalization below. So in a sense, we will see later why the, again, probably you can do it without normalization. I don't know. It's just the author's choice that the weights here in each row are sum up to 1. Okay, let's see. Now, question is, what is this function A, right? And authors present you the full formula, where actually we include softmax and whatever is inside. So we pretty much see that this part is a softmax, and this is the whole A function. Right? It somehow takes in the features, transforms them, and then applies additional transformation to what I've called previously, it's a concatenation operation. It's basically you have vector 1, vector 2. Okay, it's elementary, right? It's just stacks them together. And then you have to realize that this weight is a scalar. So in a sense, whatever this A is, this all is collapsed to a scalar. So it's basically it's a dot product of two vectors of size 2 times f, where f is a number of features, right? Of course, we will use a transpose notation. We will use how do you call it? GIT is equal to a right multiply, and then actually when we stack these GIs, I probably shouldn't work right transpose here. There's no difference if you transpose after or before concatenation. So actually we will be multiplying on the right. But the idea is here that this A is multiplied everywhere for each element. What we will do is it's a matrix, we will calculate a matrix of concatenated vectors. Then we will apply dot product here, apply ReLU, and then softmax row-wise. And then I have some code that just spoofs some fakes, some kind of graph. Here, for example, we have a feature matrix that has 3 nodes. Each node has a feature of length 2. We apply some kind of projection using a linear layer. I actually wanted to use a linear layer properly, not some kind of matrix multiplication, just to make sure that we can input some kind of known data. What I do, I change the weights of this linear layer to just scaling operator, and then we can easily interpret what this network does, or if it returns the proper values. So in this case, each row is scaled by this matrix by 2. It matches the result, expectations. And now we have to concatenate this new representation G pairwise. So we kind of have to get this structure for this matrix Gij, Gij. And well, I wish that there's certain structure in this. And well, I wish we could just broadcast, just like multiply, I don't know, 2 by 1 vector, some kind of 1 by 2, and get 2 by 2 matrix with this concatenation, but it kind of doesn't work. For concatenation, you actually have to generate all the contents. So in this case, what is our approach is that we flatten this n by n matrix into just n squared list, or just matrix also, whatever. And then we observe what is the ordering of the left and right side. And then we can concatenate them element-wise. And that's the idea. We see that left part is 1, 1, 2, 2, right part is 1, 2, 1, 2, and we just try to mimic whatever it does. In this case, this is some kind of repeat interleave and the regular repeat. And when we concatenate this Gij, right, we get this matrix. Of course, we probably want to reshape it into n by n and 2f, right? But I cannot draw it using matrices. So okay. At which stage we are? We got this matrix, and then we want to concatenate, not concatenate, we want to dot product it. We want to do this operation for all the elements. Well, in this case, it's just matrix multiplication. But we can observe that as we have written it in transposed form, it closely mimics whatever Pytorch linear does. Actually, I had the link somewhere just to make sure. Here, for example, you see how it's written. It's written as a right multiply, and actually these y and x's are their row vectors. Maybe not they are row, I mean they're kind of lists, so they probably don't have dimensions of like n by 1. They probably have dimensions of n and this type of tuple. But they also work, of course, on rows. They just they do some internal magic, of course, for it. So this is the goal. We just see that we can kind of replace this dot product with A with another linear layer, except the weights here will be just just a column vector, right? And that's what I use. I use transformation that takes 2 by features and it collapses into one. In this case, okay, I have to show like interpretable, some kind of action. In case of matrices, of course, scaling. It's easy to implement, it's easy to interpret. But in the case of projection, it's not that simple. You can maybe take only like first element, basically do sampling. I decide, okay, it's maybe easier, faster just to make attention this vector filled with ones. That means that after dot product during, it will just sum up all the elements of second vector with weights of 1, right? And we can ask what are the dimensions of these internal weights. It will say, okay, I have a column vector and our input is already reshaped n by 2 times features, and the result of matrix multiplication will leave 1 extra dimension in the end, which we just squeeze out. And we just take a look, okay, whether it works correctly. Here are the entries of the concatenated versions. We apply dot product with this, which results in sum of elements, and it is exactly what we get. Of course, this is a spoofed, like fake variant, just so make it interpretable. And idea is that this is our new weight matrix, this E. What we have to do is pass it through activation. Here it's ReLU, leaky ReLU, in my case ReLU, because they are all positive, it doesn't make any change. And now the important point is that maybe generating all the possible weights is not probably the correct idea. Maybe we have to some kind of restrict it to actual edges, right? And that's the point where we have to do some masking, basically, so we get a result of weights in the end of 0 for not connected edges. And how we do this masking is very particular for, actually, because we apply exponents, we cannot just mask exponent by, we cannot just say sum 1 1 is equal to 0, because after this soft maxing, okay, we will just exponentiate both sides and we'll get 1. It's not what we want. Actually, we want, instead of masking by zeros, we want to mask by minus infinities, so the result is like approximately 0. And this is exactly what we do here. I just generate some kind of pseudo-symmetric pseudo-adjacency matrix, and I apply this minus infinity only where the values are 0. And I get a result of this masked matrix. I apply it softmax along the neighbors rows, and I get these results. Of course, the sum is 1. Of course, it's not a linear kind of scaling normalization. We see that although like 6 and 10 are not that far away from each other, the 10 gets most of the weights. And that's pretty much the main idea, is that we replace our adjacency matrix with this new matrix that is formed from basically features, concatenated features of both nodes. And the next steps are basically the same as in convolutional network, right? With one minor change. This is the aggregation. This is the multiplication of A times H, except here actually we multiply it by our G's. So where is it? Do I have it? Well, actually, yeah. It is some kind of activation. We need aggregation, kind of lambda, whatever, not alpha or whatever. So I guess like this. Wait. Well, yeah, that's kind of interesting. Yeah, so it kind of applies weight, kind of, but we have calculated it already before. So in a sense, it does this operation. Whatever. That's the main idea. Of course, this is the simplest possible variant, because what actually authors propose is to use so-called multi-attention, multi-head attention mechanism. It means actually that our attention matrix is not the only one, that we actually calculate k different variants. And so what it means, that there are k heads. We take input data, input features, and we create k different interpretations of this data. So each node I will have g k1, k2, whatever variants. And from each of these, we construct weights using different disintention vectors. I don't know how to call it. Then softmaxing. And the math becomes, well, quite more difficult. Up until now, it was very, very simple. I won't go on it here, maybe in the next version, because you can take a look, we're only on the half the notebook. Maybe I will start with the first step, simply because I've shown you the linear algebra example of applying multiple transformations, and it's kind of convenient to be used here. Again, the idea is, we will discuss only the first step. We will create k different interpretations. So we can return basically to the previous idea. This is analogous of saying that we use k different transformations just by stacking these transformations and then applying to the original input version, and we get k different variants. Again, I use linear layer, only this time I fill it with two different transformations. One is scaling by 2, other by 4. And here is this example, our old input feature vector matrix, and then first transformation is scaled by 2, other by 4. We can transform it separately, but then we can actually stack them together on top and then apply this operation. We see we get the proper result of them being stacked. And I will go briefly without going into the math, but the general idea, actually we reshape it into new shape. So our feature matrix is not two-dimensional anymore, it's three-dimensional with additional dimension that separates different heads. And we have to generate GIJ. It becomes quite more difficult because additional dimension. Basically, we try to reconstruct the same structure as as before, except on additional dimension. It's not hard. Again, reshape it with additional dimension. We can apply the same attention vector to all, but it's not the idea, although in the reference they use this, not in the paper, but in the implementation of this. And if we want to apply, let's say, k different attention vectors to k different concatenated these representations, we'll have to do some additional maths. There are simple ways, like simple ways where we do it in few steps, or I show you that we can do this using Einstein summation and achieve this result. Or alternatively, we can do it simply by element-wise multiplication, but basically recreating. What we are required to do is to apply like element-wise dot product, and it's not a correct matrix multiplication operation. Not the correct in a sense. It's not matrix times matrix multiplication, because there's a contraction inside dimension reduction. So kind of you can mimic this behavior. Actually, you can do it probably in for loop for all the separate heads, which will be even easier. We use the same mask, and we get basically k different attention matrices, if we can call it. Now the aggregation is based on the same idea of linear combination. In this case there are additional dimension that we have to take care of. So we kind of, again, at least I use it against an Einstein summation to take care of it, right? This crazy representation, you can ignore it as long as you write a proper summation rule. You will get a proper recipe for the Einstein sum. Some testing. So again, our feature vectors now are feature matrices. We can follow that it all works out. The question is, okay, when we get this k different interpretation of data or of edges, like what the hell do we do with it? We can either concatenate it. Here's like first row is interpretation of head 1, second row of head 2, whatever, or we can take mean version, whatever. And actually, I will not explain it here because it will take some time. Yeah, but I've created, I've implemented the forward pass in this layer. There are more comments than actual code probably, but the idea, I just basically copied it out from that notebook and actually applied it to a problem that's discussed, one of the problems in that paper. I didn't achieve the same accuracy, but again, maybe I can leave it for longer. But still, the idea is it kind of works. Our self-implemented method works. So that's all. Maybe I will do a second video on details of maths for multi-head, because I would like to explain how to actually implement this Einstein summation. And thank you for listening.